Okay, pre-cal 12, here we go. Let's get after it. We are now going to take our exponential and logarithmic knowledge and then apply it to some everyday scenarios. So this is what you ask for. These are word problems. These are when would we use this? These are options of when you will see this happen. Now, obviously, when you see this stuff happen, it's oftentimes career specific, so please keep that in mind. But here we go. One of the big ones is always has to do with money because exponential growth is what we want from our money. We don't want it when we're borrowing money, but we definitely want it when we're investing money. So there's two scenarios that we're going to look at here. So we have, in this case, a monthly compounding, okay? Because you'll see the difference between this example and the next example, and the equation is slightly different, and it's demonstrated in your notes as well. So for the first one, we have monthly compounding. So again, remember, we saw this earlier in our career. We have the compound interest equation. So n equals monthly, so 12. R is our interest rate, which is given at 10%, so 0.10 or just 0.1. T in this case is our unknown. And that's what we would expect because our unknown should be in our exponent because we've been working on. My principal is $5,000, right? And his broker's giving him two different options, right? So in this case, there's some info missing from this slide. He wants $30,000. Okay, so his broker, his investor is going to give him two options. So that's what our A value is in this case. So it's missing from the slide, but it's in the notes online. So there you go. He wants 30 grand. So this is our equation. 30,000 is our A value. Our principal is 5,000. And then we get 1 plus our interest rate divided by our compounding period, and then 12 times t. So you can see this is a moment where my unknown is trapped up here in my exponent. And how do I get it down? I use logs. But before we do that, let's simplify as best we can. So algebra here, let's divide everything by 5,000. That's going to cancel that off, divided by 5,000. So now we get 6 equals 1 plus 0.10 divided by 12 to the power of 12t. So now we are doing our swap from logs to exponents work. So the log, here's the interesting one. What's the base of that log, right? Well, in order to consider that, your base of your log is going to be 1 plus that, right? Now in the notes, I've done this another way, but you can look at this way as well. So that's the base of your log. That's the object of your log, and your answer is 12t. But in order to free up that base now, you use change of base formula. Now in the notes, all I did was I took the log of both sides. And you'll see that that's essentially where we're going to end up in a few minutes, but this is just another way to look at it. I wanted to be diligent in showing a number of scenarios. So change of base law, I'm going to keep it with base 10 so I can do the calculation. But now I end up with log base 6 over, or sorry, not base 6, log of 6 over log base 10 of that whole thing in brackets. You could calculate that number out, but we could also leave it there. And that is equal to 12t. So now how do I get t? I divide both sides by 12, which is the same as multiplying by 1 over 12. So now I have t equals log base 10 of 6 over 12 times log base 10 of this lovely number. So again, this is where your computer or your calculator usage comes in handy. Make sure you key all that in properly. And if you key that in properly, you get 17.99 years, which means 18 years. So in order to make $30,000 on a $5,000 investment, given a 10% monthly compounded interest rate, 10% interest rate compounded monthly. I don't want you to think you're getting 10% every month. You're getting 10% a year divided by 12. And you get 18 years for your time result. So that is option 1. And you can see that this was the equation we used. Now option 2 changes slightly, and we introduce you to a different equation. And this is when we say you have what's called continuous compounding. And for continuous compounding, we use the equation that has the E value in it. So again, we're looking for 30 grand. And you can imagine the answer is probably going to be, or should probably be, hopefully about the same, right? About 18. And I just want to show you the two different styles of equation you can use. Because in this case, you can do the same thing. 30,000 equals 5,000, but in this case times E and then R, which is 0.10 times T. So in this case, we don't worry about N, right? Because N is continuous, and that's what gives us the E variable. Or sorry, the E constant, I should be accurate there. Now again, divide both sides by 5,000. Boom, boom, and we get 6 equals E 0.10 to the T. Now you could do the same approach we did on the last one where you convert into log form, but in this case what I'm going to do is I'm going to show you that we can just take the log of both sides. But since we're dealing with E, we don't necessarily have to take the log base 10 of both sides. Let's just default to take the natural logarithm of both sides, because now we have the natural log of 6 is the natural log of E 0.1 t. And recall that the natural log of E, those two statements cancel each other out. It's like having log base 10 of 10 is just 1, right? So that's what we get for natural log of E is just 1. So we end up with the natural log of 6 is equal to 0.1 times t. And then we divide both sides by 0.1 and 0.1, and we calculate natural log of 6 divided by 0.1 is time. And sure enough, we get 17.92, which is close enough to 18. So you get slightly less time on continuous compounding because you compound continuously rather than 12 times. So you get this subtle increase in the amount of compounding periods, which equates to about 0.08 of a year. So it doesn't make the hugest impact. But if you are a stickler, you're going to take option 2, even though they're essentially the same. So the other example of a context question we looked at in section 5.1 is the radioactivity. So we talked about half-life equations. So for this equation, again, we have a new we saw both equations the first time through, and we're going to look at them again now here. So this is our first equation option. There's no E in this one, right, or K. Remember, I'll switch to the next slide. In this equation, we had the E and the K. K was the proportional constant. We had to calculate the logarithm, and we didn't really know what we were doing. And I told you to not worry about it because we're coming back to it. Well, now is that moment. So let's do this one first. So half-life of valerium. So what does that tell us? That tells us it's half-life, so X is a half. And the half-life is 13 years. So that means the big T for time is 13 years. And what we want to know is the little t, right? We want to know how long does it take for an 80% sample of how long does it take for 80% of a 5-gram sample to decay? So we're going to lose 80% of it, which means how much is remaining? We are keeping 20%. So what does it mean though? If we have a 5-gram sample, in order for 80% of it to decay, we multiply by 0.80 and we get 1 gram. So that is going to be our final amount. And our initial amount is the full 5 grams. So now that gives us the equation. Well, 1 gram, I'm going to have 1 gram of a possible 5 grams. When it has a half-life with a decay speed of 13 years half-life, how long is it going to take for me to get down to 1 gram? So again, you can see your exponential is where we're hiding the unknown. So we got to free it from there. So let's divide both sides by 5, right? We want to isolate our exponential statement. And now we have 1 over 5 equals 1/2 t over 13. So again, you could take the log of both sides here, or we could convert this into log form. So the base of the exponential is 1/2, so the base of my log will now be 1/2. The object of my log is the answer of my exponential, so 1/5. If it helps, we'll put brackets around it. And then the answer is t over 13, my exponent. So I'm using that switcheroo from exponential to logarithm that we learned in 5.2 in order to now solve these contextualized questions. And all it takes now is creating a way I can run this through my calculator, right? Because right now I can't key in log to the 1/2 of 1/5. So change of base formula. So I got to do that because that way I can get either the natural logarithm or log base 10. We'll just go log base 10. So now I have log base 10 of 1/5 over log of 1/2, and that equals t times 13. Now you could do the funky, I'll just show it up here on the top, right? Log of 1/5 is the same as log of 5 to the -1, bring the negative down, but you created this statement you can just plug into your calculator. So what you want to do is you want to just plug that into your calculator and then multiply both sides by 13 and you're done. So go second function and then log of 1/5 and then divide that by the log of 1/2 and you get 2.32. And then we go 13 times 2.32. Let's trace that over in white so we can see it. 13 times 2.32, and that'll give us our t value. So the amount of time it takes to degrade down to 1 gram is 30.2 years. All right, so it's tying in all of the rules, and you can see that you could work this through a couple different ways, but as long as you're following the laws and the rules and all your logic is sound, you should end up in the right spot. So there's a second way of solving this one as well, and that's by using the other equation, the equation that has the e-value and the proportional constant. But again, our first step in this case is we need to solve for k, because without k, we can't do anything, right? Now, how do we get k again? We consider the fact that we're talking half-life. So how long does it take for my 5-gram sample to become 2.5 grams, half of the 5 gram, because k is my proportional constant that gives me my half-life value. So now I have 2.5 equals 5, and then e times k to the 13, or times 13, because 13 is the time it takes for me to lose half. So now I got to solve this for k. So divide both sides by 5, and you get 1/2, or 0.5, equals e, and then to the power of 13k. Now just take the natural logarithm of both sides, because remember that when you take the natural log and you have e as your object, they're going to cancel out. So you get the natural log of 0.5 equals 13k. So k equals natural log of 0.5 divided by 13. Now you could solve that through as a decimal, but you can also hold on to it as a number and plug it all into your growth decay equation now, because now we have k, now we're good to go. The rest of the question stays the same from the previous page. 80% of 5 grams was 1 gram. So now that is what I want to know, and I had 5, but now this time I have e, and now my t value is I don't know, but my k value is natural log of 0.5 divided by 13, and then that is times my unknown time. So again, divide both sides by 5, and this time you get 1/5, which is the same as 0.2. I'm converting to decimal here to just give you another option. So 0.2 equals, and now I have e to the power of natural log 0.5 over 3, all times t. And now we take the natural log of both sides, because that's going to cancel off my e value, and over 3, or sorry, 13, not a 3, it should be 13, and then times t. So now those cancel out, and I'm left with natural log of 0.2 equals the natural log of 0.5 divided by 13 times t. And then a bit of algebra here. We multiply both sides by 13, and we divide by the natural log of 0.5. We multiply by the reciprocal. Do that here as well. And now we can plug into our calculator. So we have 13 times natural log 0.2, all divided by the natural log of 0.5. And that leaves us with t, because cancel, 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 cancel. And what do we get when we crunch that into our calculator? We get 30.2 years. We get the exact same solution. If you had converted this into a numerical value and rounded, you would have gotten an answer that is slightly different because we're rounding, we're cutting off values, and it gets incorporated into our final result. But otherwise, you get the same answer. So these word problems can be challenging. They always can, because we're converting a verbal statement into mathematical speak, and then we have to do all the math that is the hard part anyways. So try your best. I only have the two examples in this note pack, but there's a whole bunch of questions for practice. So try your best. Some of the scenarios might seem unfamiliar, but think about the tools you have, think about what is being asked, and do your best to work your way through. If you're unsure, you can always throw in the comments what you'd like to see an additional video of, and I can post another one to help you out. Okay, I hope this helped. Thank you so very much. This is our last booklet for section 5. We are going to dive now into the wonderful world of trigonometry, and we're going to stay there for quite some time. So I will see you next time.